Hello students, my name is Shashank Shekhar. So let us continue with the chapter of coordination compound. So today is the second lecture. If you look at the properties here, so we have started with the introduction part. Now we'll talk about Ligands coordination number and all the terminology that are related to coordination compound. Clear? So let us start our today's discussion. So if I talk about the topics, so the topics are double salts and complexes. So we'll just try to differentiate between normal compounds and the complexes that we have. Second, we will see what is coordination entity and what it is constituted of. Third is we will see that it is constituted of central atom and ion. Second is ligand. Then we will talk about the denticity of ligand. After that, we'll talk about the types of ligand, in which we will have ambident ligand. Further, we'll move to coordination number and we will talk about coordination sphere. Then we will talk about the structure and all, and about the oxidation number of central atom. Then we will see the difference between homoleptic and heteroleptic complexes. So let us start our today's class with double salts and complexes. So if I talk about their formation, so both double salts as well as complexes are formed by the combination of two or more stable compounds in stoichiometric ratio. But they're different in the fact that double salts such as carenolite, that is having the formula of KCl.MgCl2.C6H2O, more salt FeSO4 NH4 whole twice SO4.6H2O, and potash alum, which is KLSO4 whole twice dot 2LH2O. They dissociate into simple ions completely when dissolved in water. But the complexes which are say when dissociated in water, they do not when dissolved in water, they do not dissociate completely into Fe2 plus and Cn minus ion. So this is the main difference between the double salt and complexes. Although their main way of formation is same, means they both are formed by the combination of two or more stable compound, but the former one, that is the double salt, is not is completely soluble in water, means they dissociate completely in water, while these complexes, when they are dissolved in water, they are not completely dissociated into their corresponding ions. Clear? Next, what is coordination entity? So coordination entity will constitute of central metal, that can be atom or ion both, that is bonded to a fixed number of ions or molecules. So for example, we have COCl3 NH3 whole thrice. It is a coordination entity in which the cobalt ion is bonded by 3 ammonia or surrounded by 3 ammonia and 3 chloride ions. Other examples would be NiCO4, PtCl2 and NH3 whole twice, FeCN6 whole 4 minus and CONH3 6 whole thrice, or all 3 plus. Now we can see in each of this have different components. We can have ions outside this sphere also, and we have metal ions in the coordination entity. We have again some neutral or ionic species, that is CONH3, or if we talk about ionic species, we have CN. Now let us see about all of this. What is this entity made up of? First of all, what is central atom and ion present? So if I talk about the central metal, then in the different cases we will have different central metal that is present inside the coordination sphere. Okay, and that metal ion is bonded to ions or groups in definite geometrical arrangement around it. So this should be made clear that we have seen the difference between primary and secondary valency, and there we have seen that secondary valency are directional in nature, means their arrangement is fixed. So that thing is mentioned here, that around the central metal, the ions or the group of or the groups are arranged in a certain geometrical arrangement. So for example, so if I talk about the example, so this is our central metal here. Okay, these are our side atoms, ions or groups. So here Cl2 and H2O whole 4. Then we have here cobalt as the central atom. Okay, and Cl and NH3 5 at the side at ions or groups. In this case, we have Fe as the central atom, that is iron as the central atom, and Cn as the ions or groups that is surrounding this metal ion. Clear? Now this metal central ions are also referred to as Lewis acids. Why they are called Lewis acids? Because they can accept electrons. Okay, they can give electrons. Because they are metal, so they will give electrons. Now if I talk about the ligands, so you must have seen we have ions or groups that is surrounding our central atom. Okay, so here we have, say, the example of H2O. We can have NH3 as the ligand, we can have Cl minus as the ligand, or we can have larger molecules such as this as the ligand, or we can even have macromolecules, this very large molecules I would say, that is present in case of proteins. So if I talk about ligands, so ligands are molecules that donate a pair of ion to metal ions. Okay, so they are donating a pair of electron to the metal ion. If we talk about their classification, so they can be of three types: neutral, ionic, and cationic. So this classification is on the basis of charge they carry. So if they are neutral, means they have no charge. So the examples are H2O. We know that it is a neutral molecule by the balancing of charge. We have NH3, we have CO. So all these three are what? Neutral molecules. If I talk about anionic, that is containing negative charge, then we have the example of chlorine minus, OH minus, and Cn minus. So all these three are what? Negatively charged. Then we can have cationic charge, positive charge, that is NH2 plus or NO plus. So these are the classifications of our ligands. Next is denticity. What is denticity? So now we have seen many of these things. We have seen that we have a central atom, and we have seen that we have ions surrounding the central atom that is satisfying the secondary valency. Okay, and we have seen that those ions or that groups are donating electron to the central atom. Now since they are directly bonded to the central atom, there must be a specific atom inside that group or inside that ion that would be donating electrons. So let us assume that we have a ligand, say AB and C. Now there is a chance that A can donate electron, or A or B both can donate electron, or A, B, C, all of these three can donate electrons. Now the number of sites that are available in a ligand that are available for donating electron, it's termed as its denticity. Okay, so if I talk about each of this molecule, we have water here. Now hydrogen have no lone pair. Okay, so it will donate electrons, which will this atom will donate electron, that is oxygen. If I talk about ammonia, again hydrogen are not good for donating electrons, so nitrogen will be the one which will be donating electrons. If I talk about Cn minus, so there will be a negative sign here. Okay, so again this nitrogen has lone pair, so it will donate electron. In case of a single atom, so Cl is the one donating the electron. And in case of pyridine, nitrogen is the one which is donating electrons. So in all of this, you can see that there is only one site of donation. So they are called as monodentate ligand. Clear? Next, let us see some examples of bidentate ligand. So bidentate means which can donate through two sites. So here we have the example of ethylene diamine. Example of ethylene diamine, which is also abbreviated as EN sometimes. Now in this molecule, we can see that there are two sites that are present for donation, that are nitrogen, this nitrogen and this nitrogen. So this both sites can donate electrons. So it is an example of bidentate ligand. It is an example of bidentate ligand. Next is the example of bidentate. Next example is of this, that is acetyl acetonate. Acetyl acetonate. So here we can see that we have acetyl group here, CH3CO. Okay, and we have acetone group here. Now if you see here, this is for acetonate and this is for acetyl. Means if we just combine this name, acetyl acetonate. Now here, two sites are available for donation. Which are those two sites? This oxygen has lone pair and this oxygen is also lone pair. So they both can donate to the central atom. Next is the example of oxalato. So this is coming from oxalic acid, which looks like this. So this is your oxalato. Now, if you remove one hydrogen from here, then that would result in oxalato, that is this molecule. Now again, this molecule has two sites of donation, this one and this one. So it is also bidentate. Now we can have polydentate, which has multiple sites of donation. Now if you want, you can term it as tridentate also, no problem in that. So we have used a general terminology, that is polydentate, for ligand having greater than 2 denticity. This is called ethylene diamine tetraacetate, which is hexadentate. Hexadentate. It can donate to 6 sites. So it is a very popular molecule that is used for analysis. Now if I talk about tridentate, here are the 3 sites of donation: this nitrogen, and this nitrogen. All these 3 sites can donate. Now you will see an example later on that although the one we will see will have 2 sites of donation, but it will not be termed as bidentate. So the reason behind it, that the distinction is very clear, that these 3 sites are available at the same time for donation. Means if there is a metal ion here, then both of these sites will be donating electron at the same time. Here also, if you have a metal ion, then it can donate at the same time. Now here is the example of hexadentate. How is it hexadentate? First of all this negative charge 1, 2, 3 and 4. Now two more sites should be there. So they are this nitrogen and this nitrogen. So if you want to draw it, you can draw it in this way. So we have a CH2 here. Okay. So how you would donate it? So we have ethylene diamine tetraacetate. So this is the ethylene group. This is your ethylene group. This is your ethylene group. And about tetraacetate, so these are the 4 acetate, 1, 2, 3, 4, and this is your diamine, this amine and this amine. So if you write it here, CH2, CH2. Okay. Now we have a nitrogen at both of this and one C at here. So we have one CH2 CO minus. Okay. We have one nitrogen here. We have one nitrogen here. That is again bonded to 2 acetate group. Next is this. So we have N here, we have F placed here. Now this C can make one more group, that is your nitrogen and CH2 COO minus. CH2 COO minus. Now these are the sites 1, 2, 3, 4, 5, 6. So this is hexadentate. So this is the only example of hexadentate that you have to study, which is ethylene diamine tetraacetate, which has a charge of 4 minus, because 4 oxygens are there which have a negative charge. So charge of 4 minus. It is abbreviated as EDTA. Clear? Now let us talk about ambidendant ligand. So I have told you earlier that if one of the if ligand has 2 sites of donation, but they are donating at the same time simultaneously, then they are termed as bidentate. Why I have mentioned it, you will see it here. So if you talk about nitrito, so it can have 2 sites of donation, oxygen and nitrogen. But the difficulty here is that it can donate through only one site at a time. Means both of the nitrogen and oxygen cannot donate to the metal ion simultaneously. So such ligands which can donate at one from 2 sites, but one time at to one metal atom at one time, then we will term it as ambident ligand. So definition says that molecules or ions that can donate a pair of electron to electrophile from two different atoms are termed as ambident ligand. So here you can see that we have nitrito, nitrito N and nitrito O. So when we say nitrito N, then the donation site is nitrogen. When we say nitrito O, the donation site is oxygen. Clear? Now if I talk about the bonding here, then you can see that this nitrogen is giving electron to this metal. Now it is giving electron to its metal, so it cannot form one more bond here very efficiently. So what does it do? It just donate the pair of electron to oxygen, and now oxygen has a complete valency. So therefore it will not donate electrons. Here the oxygen does not have a complete valency. It has a negative charge here, so it will donate its electron to the metal. Second, we have cyno. So here cyno and isocyno. Cyno has a donation site as carbon, and isocyno has a donation site as nitrogen. Okay, clear? So in cyno, you can see that nitrogen has a complete valency, but carbon has a one electron pair here. Whereas in isocyno, nitrogen valency is not complete, and hence it can donate electron. Then we have thiocyanito and isothiocyanito. In thiocyanito, what we have is that we have sulfur as the donating site, where in case of isothiocyanito, nitrogen is a donation site. Okay, so here is just the placement of electron different, means the electrons are placed differently. So if I just try to write it, they both are nothing but a resonance structure of each other. This was the first structure, this is the second structure. So how it would have been formed? Nothing new has been occurred here, only this had been donated here and this negative charge has been developed here. Okay, clear? Next is thiosulfato and thiosulfato S and thiosulfato O. So similarly, if sulfur is the donating atom, then it is termed as thiocyanito S, and if oxygen is the donating atom, then it is termed as thiosulfato O. Again, these both are resonance structure of each other. We have just pushed this electron here and created a negative charge on this sulfur, and this oxygen is having a negative charge which is placed here, and there is a double bond between oxygen, and C, sulfur is donating electron. So these are the 4 examples of, say, ambident ligand. You should remember all of this by the structure, by the name of this, means you should remember along with its structure, not alone its name. Next is coordination number. Now we have seen that we have ligands, we have a central atom, and ligands have multiple sites, and it can have 2 different sites depending upon the resonance structure we are dealing with, which therefore we term them as ambident ligand. Now we'll talk about coordination number, which is the number of ligand that is attached to the metal ion. So here is an example. We have PtCl6. So here 6 chlorine atoms are attached to Pt, therefore it has a coordination number of 6. Next is NiNH3 whole 4 2 plus. So again 4 ammonia molecule can be attached to this nickel, so therefore it has a coordination number of 4. So here it is written, platinum has a coordination number of 6 and nickel has a coordination number of 4. Similarly, in this complex where C2O4 is present, now I will ask you, what type of ligand was C2O4? It is nothing but oxalato, and there are 3 oxalato, and you know that one oxalato can donate from 2 sites. So 3 will donate from 3 into 2, that is 6 sites. So what is the coordination number of iron here? 6. Clear? So that is the reason you should know about the structure and about the monodentate, bidentate and tridentate ligand. Next is ethylene diamine. You have seen this, I've told you the name, and this is the abbreviated form. Now again, I have mentioned that ethylene diamine can donate through 2 sites. Okay, so 2 multiplied by 3, again it has a coordination number of, this cobalt has a coordination number of 6. Now the coordination number we have seen, it can be 6 or 4. So depending upon the coordination number, it will adopt various geometries. Here you can see we have 5 geometries. So for coordination number 6, we will have octahedral. For 4, we can have tetrahedral and square planar both. For 5, we will have trigonal bipyramidal. And for a square pyramidal, we will have 5 coordination number. So this both will have same coordination number. This both will have same coordination number, and this will have 6. Now in this 12 syllabus, you have to just focus on only on these 3 geometries, because most of the coordination compound will be formed from these 3 geometries, that is octahedral, tetrahedral, and sometimes square planar. Next, coordination sphere. The central metal atom or ion and the ligand attached to it enclosed in a bracket, and this is collectively known as coordination sphere. So this entity that is present inside this is termed as coordination sphere. And the ionizal group that is present outside are called the counter ions. This is called as counter ions. So for example, in this compound, the coordination sphere is this, and the counter ion is K+. Now where is this charge coming from? Wow, how we will decide the charge? We will see it in the next slide. Next is polyhedron. So just now we have seen that for different coordination number, we have different type of spatial arrangements. Where we have seen that if the coordination number is 6, we can have octahedral. If the coordination number is 4, we can have tetrahedral as well as say square planar. If the coordination number is 5, we can have trigonal, bipyramidal, and square pyramidal. And the coordination number is 6, we can have this shape as octahedral. Now the most common coordination polyhedra, as I've told you, are these 3: square planar, octahedral, and tetrahedral, and we will talk about these 3 more. So for example, we have this as octahedral, this as tetrahedral, and this as square planar. Now the main confusion comes between whether the geometry will be tetrahedral or square planar. So we will talk about this, that how you will decide this. Now this is very important. What is oxidation number of central atom and how you will calculate it? So if I talk about the oxidation number of central atom, that it is the charge that is present on the metal ion if all the ligand and your counter ions are removed. Okay, so if all those side things are removed, so that would result in say your charged metal. So the oxidation number is represented by a Roman numeral parenthesis following the coordination entity. So for example, if you want to write copper, then we will write it as copper 1. So this is inside the parenthesis written 1. Okay, because here it has a charge of +1. How we'll calculate it? Let us see a very good example for it. So you can see that here we have this species and here we have this species. Now how we'll calculate it? Say, so for this, first you have to consider that overall this and this are electroneutral. Okay, so this is balancing this. So how I will calculate it? So suppose we are assuming that it is having a charge of Cn. Cn will have a charge of -1. So -2. Okay, and we know that Au will have a oxidation state of +1. So therefore, +1 and -2 will give us -1. Now overall charge on this entity should be equal to +1. Therefore, let X be the oxidation state of cobalt. So X plus 2 into 0, because NH3 carries 0 charge. NO2 also carries -1 charge. So 1 NO2 means -1, and Cl carries -1 charge. That should be equals to +1. Now if you just solve it for by adjusting the LHS and RHS, you will get the value of X as +3. Now you can try to calculate it for this also. So CuCN4 whole 3 minus CuCN4 whole whole 3 minus. Now let us first assume that the charge on Cu is X. So let the charge on let the charge on Cu is equals to X, and we know that charge on Cn is -1. Now if I add the charge of all of these, that should be equal to 3 minus. because overall charge is 3 minus, so we will write it as X, that is the charge on copper. Since one copper is present, so we will write only X. Now 4 CNs are present. Now each CN has a charge of -1. So until it is written CN, we will consider it as cyano. If it was written in this form, suppose this is written in this order N and C, then we will consider it as isocyano. Clear? So one cyano has a charge of -1, therefore -1, and this overall charge should be equal to -3. So 4 1 is 4, that is equals to -4 is equals to -3, which will give us X is equals to +1. So this thing is written here also, that copper will have oxidation state of +1. Now you can calculate it for multiple metal ion. Suppose we have this. Okay, so let us calculate it for this. So let us assume that the charge on platinum is X. What is the charge on one chlorine? We have seen it is -1. So 2 chlorines are there. So -1 into 2. Ammonia has a charge of 0. And overall charge on this complex is 0. So this will be equals to 0. That would give X is equals to +2. Okay, X is equals to +2. So here platinum has a charge of +2. What about this? So carbonyl has a charge of 0. You should remember all of this. Okay, so which has a charge of which you should remember, right? So X plus, let X be a charge on nickel, 4CO, that has a charge of 0, that is equals to 0, that gives X is equals to 0. So this has a 0 charge. Next is FeCN6 whole 4 minus. So let's charge on again iron BX 6CN, so 6 into -1, that has an overall charge of 4 minus, or sorry, -4. Now if you write it -4 plus 6, that would give it +2. Here CO has a charge of, let BX, let NH3 has a charge of 0, ammonia is a neutral molecule, and overall charge is given 3 plus. So that would bring us to +3. So this is +3. Now I would suggest you to try to find the oxidation number for any complex that you see, and that is a good practice to do. Now let us move to our last topic of today, that is homoleptic and heteroleptic complexes. So very easy to understand. So if a metal ion is only bonded to one type of donor atom, okay, if it is bonded to only one type of donor atom, then we will say that this is a homoleptic. So here is an example. So there are ammonia molecules that are present as ligand. So it is a homoleptic complex. Whereas in case of this CONH3 whole 4 Cl2, it has two type of ligand, ammonia and chlorine. So it is heteroleptic. Now let us classify these complexes also. So this is again homoleptic, only carbonyl is present. This is heteroleptic because chlorine and ammonia both are present. This is homoleptic because only CN is present, and this is also what? Homoleptic, only ammonia is present. Clear? So let us sum up all of this say terms in one diagram. So that diagram is this. Okay, so this is your overall diagram. Overall, this is called as coordination complex. Okay, so here is a molecular diagram for the same. Now this is the coordination sphere, which is present under square brackets. We have chromium as the central atom, H2O as the ligands. They are neutral ligands, and the overall charge on chromium will be +3 if you calculate it. See, H2O has a charge of 0, 6 H2Os are there, so 6, that is +3. If X was the charge on say chromium, that would give us +3. Okay, so the charge on chromium is +3, so oxidation number of chromium is +3. Now the counter ion that is present as Cl minus. So there are 3 Cl minus that would balance exactly the 3 plus charge, and therefore the overall complex will be neutral. Clear? So this is the molecular diagram for this. So you can see, do not consider this as the geometry. Okay, we do not see the geometry of the ligand, we only see the geometry of the central atom. See, it is octahedral. You can see very clearly that this is octahedral. On one plane we have these 4 ligands, and on up and on down side we have other two ligands. Clear? Now this Cl minus can be present anywhere accordingly, that is energetically favored. Okay, and it will be non-directional, as I've told you that this is a primary valency and it is non-directional in nature and it can be present anywhere. Whereas this, say this our ligands which are directional, which is satisfying the secondary valency, they are present in certain direction or certain spatial arrangement. Clear? So this was for today's class. We would end our lecture here. We will talk about more of this in the next lecture. Thank you.